Here's my big ass book of integral series and products. And it's pretty popular back in graduate school. I'm looking for the one I found before, a nice trigonometric series that gives you a result involving pi. Here it is. It's an infinite sum of sine of kx over k, which is equal to pi minus x over 2. Here's the series again. I switched to using I for the summation variable. So I here is not the imaginary unit, just the dummy variable for the series. The sum from I equals 1 to infinity of sine of ix over I is equal to pi minus x over 2. For our numerical experiments, we'll specialize to the case of x equals 1, and that gives us the sum of sine of I over I equals pi minus 1 over 2. Here we have Python already open in one of my terminal windows, and I've already typed in the program that we need. We do need to import the math library to get the sine function and the number pi. We define our function in Python using the def statement. N will be the argument giving the number of terms in the series. We want to start with the small numbers and add to them the larger numbers. That's why this range here goes backwards. And when we're all done, we'll print the result in the accumulated variable sum. Just for reference, this is our target value, what we get if we sum an infinite number of terms, pi minus 1 over 2. So let's see what happens if we start with just 10 terms in the series. It's not very good as expected. 100 gives us a couple of digits of significance. 1,000 terms in the series gives us a few. This is the precision that we expect for this 1 over I dependent infinite series. Let's see what we get if we just use a ridiculous number of terms. Say 1 billion, or for my friends outside of the United States, 1,000 million terms. So 1 followed by 9 zeros. I'll avoid using scientific notation for now. Naturally, these 1 billion evaluations of the sine function and 1 billion divisions and so on will take a while. While we're waiting, let's start up Julia in another window. This will serve to show some of the differences between Julia and Python syntax. We define a function using the function keyword. The rest of the function will have the same structure as the one we defined over in Python. This is our for loop, where we add up the terms in the series, again going backwards from smaller terms to larger terms, accumulating the result in the sum variable. And that's the definition of the function, almost the same as in Python with some differences in syntax. Let's define our target for reference again, pi minus 1 over 2. That's what we'll get if we can sum up an infinite number of terms. And let's check the result. This one agrees with the same calculation in Python as it should. All the numbers should be the same if I haven't made any mistakes, since both languages, I think, use IEEE floating point arithmetic. And they also agree for 1,000 terms. Well, let's go for broke and try 1 billion terms. Of course, this will also take a while. Notice we're using version 1.10 of Julia. Version 1.11 is about to be released. So this is already about a year old, almost a year old. To get more information about Julia, you can go to julialang.org. From there are links to documentation and other items of interest. Let's take a look at some other of the syntax differences between Julia and Python. In the notation for intervals, we can actually end on the number we want to end on instead of one less than that number, as we have to do in Python using the range function. We use the end keyword to terminate blocks because in Julia there's no white space significance. So unlike in Python, we can't depend on indentation for syntax. Although I do use indentation, as you can see, it's just simply for clarity of reading. And we can get our result just by invoking the name sum. We don't have to have a print statement. The REPL tells us after we define a function that it's a function with one method. If we define another function with the same name but a different type signature, that accepted a parameter with a different type, we would have the same function name, but with the second method. And notice here that we can also use the Greek letter pi. We can also use other Greek letters and Unicode symbols. I happen to like that. Some people can't stand it. But for me, it makes our code, our programs, look more like mathematics. Here we can see that Julia is already finished, adding up the 1 billion terms of the series. It's accurate to about 9 significant figures, about 9 digits, which is what we should expect. Let's take a graphical look at the way this series converges. We'll import the plotting library, one of many plotting libraries, but the one that I think is most popular still. And I'll also import something called Kitty Terminal Images that allows me to see full color, full resolution plots embedded right in the REPL. It only works with the Kitty Terminal emulator, but that's the one I use. Let's define our capital N to be the maximum number of terms that we're interested in, and our small n will go from, say, 4 to that maximum number in using 100 steps. So we're going to sum up this term in 100 different partial terms, partial sums. And let's take a look at how these partial sums converge to what we know is the correct answer. This ss.m, ss dot syntax magically converts our ss function into a function over vectors. So it will operate term-wise over the array, over the vector n, small n. And the keyword argument LW equals 2 makes the line width a little bit thicker than default. I'd like this plot to be a little bigger. Kitty Terminal Images lets me scale the plots up a little. So let me repeat the previous plot command at a larger size. And there you can see the way the partial sums converge in an oscillatory manner to something. Do they converge to the correct thing? Let's plot a horizontal line as a reference line to see where this sum is converging. And we'll also use a thicker line width. The result shows us that the function is converging to the correct answer slowly and oscillates over it. That exclamation point at the end of this plot function is a different function that is a mutating plot function that mutates what? The previous plot. So you can keep adding things onto the plot just by using mutating functions. And there's our horizontal line going from 4 to n on the x-axis and having the value t, or target, on the vertical axis. See the semicolon here? It separates positional arguments from keyword arguments in functions in Julia. Well, I'm not going to spend too much time here waiting for Python to finish. The spoiler alert, in about 5 or 6 minutes, the Python function completes and prints the correct result. In order to enable you to learn and apply Julia, I've written Practical Julia. It's divided into 2 parts. The first introduces you to the language and assumes only a beginner's experience with programming. The second part delves into various applications from science, mathematics, and engineering. Some examples from the book are this physics simulation of the convective motion of a layer of water heated from below. This predator-prey simulation. Will the prey species evolve fast enough to avoid extinction? Read the book to find out. Animated diagrams defined in code, such as this example from Ancient Astronomy. Signal processing, image processing for biology and other applications, mathematics, statistics, data analysis, complex graph layouts and recipes, a pandemic simulation, and much more. Practical Julia has gotten rave reviews, and not only from my friends and family. Let me show you how you can have fun with technical programming without settling for compromises in performance.